When I can start?
You can start.
Okay. Hello, everyone. My name is Giorgio Farina, and the talk today is about real-time cloud between vision and reality. So this is my background. Let me one second. I think it's better in this way. So this is my background. I did my PhD at the University Federico II of Napoli. I worked on real-time systems in Kaiserslautern in Germany, and then I did my research scholar at Purdue University, and now I'm a postdoc in cybersecurity with Stefano Zacchiroli, working on software composition analysis. So what is the real-time cloud vision? The idea is to port critical applications in cloud. That means basically when we have these robots or control laws that that run, for instance, in critical systems, the idea is to leverage the benefits of cloud computing, like elasticity, huge quantity of resources. But as you can imagine, we have different problems, especially because in these cloud platforms, we can have timing faults and also functional security faults. And these can cause the robot to failure. And so that probably they risk to not hit their deadline. And so we can have also problems to the human safety. Of course, we have different sources of interference, like connection, like the network connection, and but also on the nodes, we can have interference in terms of hardware resources and the software layer. In particular, in this presentation, we will focus on the shared hardware resources, so on the interference due to, for instance, peripherals, memory bandwidth, and shared cache. Especially, we will focus on the work where I contributed, so on the memory bandwidth. And about the shared software layer, we know that there are different solutions, but we will focus on hardware virtualization. And we'll focus on the security of these hypervisors that are basically the shared, as we can see from this figure, the shared software layer between virtual machines, okay? So this is the overview of the presentation. At the beginning, we will focus on the memory bandwidth regulation because, of course, we can have these critical applications usually have time constraints, and we need that we need guarantees on the worst case execution time of these applications. And one of the main problem is the shared DRAM. In addition to the shared cache and the bus and all the resources that we have in cloud computing, but we'll focus on memory bandwidth. In particular, we focus on this new technology that is Intel MBA, Intel Memory Bandwidth Allocator. After that, we introduce, once we have predictability, we have the problem of efficiency, because usually when we include technologies that enable predictability, we lose in terms of efficiency. And we introduce this approach that I proposed that leverages the memory queue occupancy of the DRAM to improve the efficiency. And after that, we will focus on the security of cloud computing, especially on the hardware virtualization that is assisted by hardware in this moment, and in particular on fuzzing techniques. After that, I think we have the time for discussion of our problems. So let's start from this first problem. So here the problem, what is it? So as we can see, we can have a different virtual machine in cloud. And one of them could be, for instance, critical, so that hosts critical applications. We can have problems because one of the non-critical virtual machine can interfere with the critical virtual machine by coaccessing to the memory. And so, as we can see, for instance, in this case, the worst case execution time of a critical core can increase its latency. And so we can have an increasing of the latency, especially of the memory fetching latency. And so this is a problem because we need the bound and we need guarantees in terms of latencies for time critical applications. So in literature, of course, there are a lot of software-based approaches like resource reservation, resource limitation, execution models, but all of them have huge limitations. In particular, they affect the overall utilization of the architecture, for instance, or they are they have a low flexibility. For instance, the main approaches, the main software-based approaches like bank partitioning, that is a resource reservation approach. The idea is to allocate different banks, memory banks, to the virtual machines. But in that case, it's a problem. It's not easy because usually hardware vendors don't disclose this kind of the memory mapping, okay, the memory bank mapping. So we need first to reverse engineer the mapping, and then we can try to map these memory banks by using the page table. Instead, a more flexible approach is a resource limitation. So the idea is to limit the number of requests, of memory requests within a regulation period for every core. But in that case, we have problems in terms of efficiency because when a physical core finishes its budget, we need to stop the execution of the core. Okay, so we lose in terms of resource utilization, even though that core could run in its private context, for instance, on its private cache, on the data that are in the private cache. And in addition, they don't consider the synchronous memory accesses. Finally, we have the execution model that is the more intrusive problem, where the idea is instead modify the programs. So for instance, by using a compilation, by modify the code that run in the cloud, but in order to co-schedule memory fetching phases and to control the degree of interference. But of course, this solution is intrusive. So fortunately, hardware vendors, yeah. As you, I don't know usually how do you do, yeah, by, okay.
The third option requires that all the programs that run in parallel with the third approach should be co-written.
Yeah, exactly. Not co-written, but you need to modify this the code, the binary code, also the executable maybe, in order to group together memory accesses, and in that way you can co-schedule the memory fetching phase of
so you have to have control about
all the
virtual machines.
And it can work if you have control, if it is your architecture, but is not good for a cloud paradigm.
Exactly. Okay, thank you.
Yeah. So fortunately, hardware vendors started to understand the problem. So they start to introduce hardware features in order to handle this problem. For instance, the new Xeon Scalable server support this MBA, inter-memory bandwidth allocator. And basically, as we can see from this slide, they introduce delays, configurable delays between the requests that go from a physical core, a CPU, versus to the shared context, so versus to the bus, okay? And so we have an indirect limitation to the DRAM. Of course, we have several advantages, like it is easy to reconfigure because we can reconfigure the MBA just modifying a model-specific register. It never stops the core execution because it introduces some delays, but we don't stop the execution. And it is not intrusive. It's completely transparent to the virtual machine and to the core, to the containers, whatever you want. The problem is that it is a black box hardware controller. So we need a systematic evaluation of this controller because it is described, its behavior is described in only 2 pages of the reference manual of Intel. And so it is hard to rely on this hardware controller. And the second thing is that we have different possible delays. So we have to estimate what is the real limitation that we have. And the third point is that it is an indirect limitation. So as we can see, from the MBA to the DRAM, there is a bus, there is a last level cache. So we have a different optimization layers. And so we don't know what is the actual delay that we have on the DRAM. So for instance, if we use a classical DRAM bomb workload, where the idea is to allocate the large memory, dynamic memory, read loop this memory in order that, because it's bigger than cache, we have a last level cache miss. Okay, it's the classical way to create last level cache miss, so access to the memory. This is good because we can measure that the 90 delay have a 75% of limitation. So the requests to the memory are delayed of 75%. So we have an increase in the latency of 75%. This is good. But I did this latency sensitive analysis. So instead of allocating a larger memory and then read this memory in loop, I did a sensitive analysis. So what I did is using CL flash, where we can make the flash of the memory in order that we are sure that every access causes a last level cache miss. And we can see that that regulation is bypassed in a specific setting at the beginning. So we introduce this benchmark to evaluate the direct limitation of this MBA. And in particular, we introduce this new workload, exclusive DRAM bomb. Why? Because in this workload, we are able to generate memory requests from a core, from a physical core, without generating L2 write back. Now you can think, okay, but why you have L2 write back if you are not doing writes? Because it is an exclusive cache, okay, it's not inclusive. And so we can have in private cache line of data that are not in the last level cache, and so we have the write back, okay? And so, as you can see, this is the workload, that exclusive one, and we can see that we don't have a lot of writebacks. Instead, on the DRAM workload, the DRAM bomb workload, we have a lot of writebacks, and we can see that we have half of the LVID the regulation. Okay, and so this is a very important result, because this means that we cannot use generic workloads that exist for evaluating a specialized controller, but we need a more detailed analysis. Once we have the per core indirect limitation for every delay, we can use, of course, the existing predictive model in order to predict the regulation based on the degree of interference, so on how many core are interfering, okay? Now we have another problem, because, okay, we can apply this delay, but when we apply this delay, it's a static delay. And so we lose in terms of resource utilization, because if we apply this delay and maybe there isn't interference, we are not using the entire memory bandwidth. Okay, so this is a problem. because of course in cloud, we want to leverage all the available resources. And so we propose this new approach, a detection regulation approach. So the idea is instead to detect the memory bandwidth interference. So only when we have interference, we apply the regulation. Okay, what is the interference in for the memory bandwidth? The degree of interference is the number of core that are co-accessing to the memory. So we need a way to detect how many cores are co-accessing to the memory. For instance, we can calculate the worst case execution time by saying, okay, I'm able to have this degree of interference. So at the most, when you access to the memory, can be other 3 core that are co-accessing to the memory. So we need to detect this degree of interference. How can we detect this? We did this hypothesis. So our idea is we can use the occupancy. Why? Because we believe, so in our hypothesis, we think that exactly by monitoring the memory queue occupancy, we are able to infer the number of interfering core. So how many co-accessing core exist to the memory, are actually working on to the memory. And why it is a good hypothesis? Because we know from theory that every core has a limited number of pending requests. Okay, so when you have a core and you start to make in loop requests versus address it to the shared context, you have a limited number of requests. You cannot start to put in infinite requests. Okay, so you have a bounded number of requests. And this means that when we have 2 core, at the most on the queue, we can reach a specific threshold. Okay, and when we have 3 core, we have a bigger number of possible requests versus to the memory. And so we started to evaluate this hypothesis, and in Intel Xeon processors, there is this event, memory queue occupancy, that stores the number of cycles that the memory queue holds at least any request, and we could configure these requests. And as we can see, in fact, when we have, this is, in this figure, is represented the portion of the regulation time of the regulation period, that is 1 millisecond. So what we do is, we have a regulation period that is 1 millisecond. At the beginning of the regulation period, we reset the program counter. So we reset this event. And we capture this event at the end of the regulation period, so after 1 millisecond. And this performance counter stores the number of cycles that the memory queue occupants, the memory queue, hold it at least any request. Okay, so as we can see from this figure, in this figure we have the percentage of regulation period that the queue hold it at least 16 requests. And when we have a 3 core, for just 1/6 of the regulation period, the queue holded 16 requests. Instead, when we have a 4, 5, 6 score for the entire regulation period. So we can use this metric to detect the number of interference core. And so we can set a threshold because this performance counter allows to set up a threshold. And when we pass this threshold, we can apply the MBA. And it works because we are able to detect more than 2, 3, 4, 5, 6 core that are co-accessing to the memory. And in the worst case, we need 1/5 of the regulation period to detect this interference. Okay. So this is now let's go to the secure cloud, okay? Because if we move a critical application to the cloud, we have also the problem of security. Because if we run our critical applications on our local devices, we don't have these issues, right? So I mean, we have these issues, but we are not so connected with the other customers. And instead in cloud, what happens is this one. So we have usually two kind of resource virtualization technologies: operating system virtualization, where the operating system is virtualized, or we have hardware virtualization, where the hardware layer is virtualized. And so we have different virtual machines. We are in the second case, so in hardware virtualization. And as you can see, we have a shared software layer that is the hypervisor. So even though currently the hardware virtualization is assisted by hardware, so we have VTX and or other technologies in other hardware vendors, we have still the hypervisor intervention, okay? For missing hardware features or for device virtualization. And so there is a C software intervention. And oh, wait, no. And so we have also different hypervisors, different solutions from cloud to the embedded systems. And we have these different solutions based on the trade-off that we are looking for. So between security, predictability, efficiency, and so on. And as you can see, we have also different intervention of the hypervisor based on the target hypervisor. So if we are like analyzing JLAUS, that is for embedding systems, so is a static partitioning hypervisor, we have a few hypervisor intervention. Instead, if we analyze a KVM, that is, for instance, the technology used from Amazon, okay? We have a lot of hypervisor intervention also when we have I/O workloads, especially when we have I/O workloads. So what is the threat model? The threat model is this one. So as I told you, we can have different customers in cloud, everyone with his virtual machine. And as you can see from a virtual machine, we can attack the hardware virtualization interface, virtualized interface, in order to exploit bugs within the hypervisor layer and cause problems to the other virtual machines that are co-located on the same hardware platform. So in this figure, you can see the malicious entities, the target, so that is the hypervisor layer, the attack vectors, and where we are looking vulnerabilities. And the hypervisor runs in root mode or in user space or in kernel space. So why is it challenging to test these technologies, hypervisor intervention? Because as you can see, we can have a virtual machine with its virtual CPU and virtual memory. And when we have an hypervisor intervention, so the hypervisor execution, the hypervisor can read the entire virtual CPU or virtual memory of the virtual machine. And so we have a very huge attack surface. The entire memory of the virtual machine can be potentially an input for the hypervisor intervention. And so it's big. And then it's also dynamic, as we have seen the previous slide, because we can have the hypervisor can configure in different way what are the virtual machine conditions that cause virtual machine exit. It is complex because we have a grammar within the hypervisor, and the inputs are connected each other, are linked, and it is stateful, so a virtual machine exit can depend on previous virtual machine exits. And then we have the diversity. So we need also a solution that is portable, that is transparent to the target. This is an example of a CPU virtualization. So as you can see, for instance, we have at the beginning a guest instruction, like a move to a guest virtual address, okay? And this guest virtual address is translated in guest physical address. And this page of the where it is this guest physical address is flagged as without permissions. And so we have the virtual machine exit. We have the hypervisor intervention, and we start with instruction. We need to, it has to start with instruction decoding, because for the extended page table violations or misconfig, we don't have enough informations about what is the operation that the target was doing. And so we need the hypervisor needs to decode the instruction so as to access to the memory of the virtual machine to fetch the instruction. And to do this, has to first access to the virtual CPU to understand in which state the CPU is. And for instance, is in paging mode. Then as to fetch the instruction, so as to navigate, as to walk the entire page, the page table of the guest. And so there are other accesses to the memory of the guest. And then we have the instruction fetching. After that, we have the emulation. And the emulation, for instance, in this case, can be also device virtualization. For instance, it can emulate a peripheral access. And then we have the virtual machine entry. In fact, this is device virtualization. So during emulation, we can have a device virtualization. Opposite to CPU virtualization, this runs in user space, not in kernel space. And for instance, the operating system can be also para-virtualized with the virtual. So it's another way to communicate with the shared memory. But the hypervisor intervention is always called in this way, so through a virtual machine exit. And the problem in device virtualization is that, for instance, during the emulation, the hypervisor can access to the memory to read inputs of the guest, like emulating a DMA access. And these accesses, as you can see, can be connected and structured. And so it's very hard to modify these inputs. And another problem is that for DMA accesses, so for device virtualization, these accesses are also asynchronous, so can be postponed in next virtual machine exit. So this is the work inside that idea, that our contribution. So we propose the IRIS for CPU virtualization, published at the DSN. Where the idea was after our paper, there is Hyper Mirage that basically it published at NDSS. It's not our paper, but they start from our work and they introduce a symbolic execution, and it is published at NDSS. So what is the problem that we try to resolve? So creating for CPU virtualization is very hard to generate workloads because you need the knowledge basically of the operating system. So for instance, you have to go to protected mode, and then you have to create, you have to create a guest workload that, for instance, switch in protected mode, and then an extraction that is sensitive, and so you call the hypervisor intervention, okay? So they are not easy to create these test cases. In fact, hypervisor was started from manually created starting virtual machine states. And so our idea was, okay, instead of manually creating virtual machine states, we can learn from the execution of the guest workload, of the guest virtual machine. So we can, for instance, in this slide, you can see that we are running, is not, there is a mistake, is Linux that runs in Xen. This is the the boot of Linux in Xen. And we can see that we have 500,000 of virtual machine exit. And so our idea is, okay, these are already test cases. We can learn from these accesses, okay? We can start from these. But how can we record these accesses? So, of course, we cannot, we need a way to record and replay efficiently these accesses. And we can start from these intuition. So we have a guest workload, okay? So imagine that you have the operating system running in a virtual machine. But when you have the hypervisor intervention, you have a context switch. And during the virtual machine exit, as you can see from this slide, the hypervisor read an abstraction of the virtual CPU and other information that are generated from hardware, that is the virtual machine control structure. Then it can read the general purpose register and the memory of the virtual machine. And so what we need to read, we need to read the inputs to the hypervisor. And so this is Iris. So what we do is we have a virtual machine that run a workload. We register the inputs to the hypervisor. We collect test cases. And then we reply only the inputs without the guest workload. Okay, putting the inputs to the hardware interface. And in this way, we have two advantages. The first one is that we have a performance gain because we are not running the guest workloads. And so, for instance, I don't have here the example, but also the workload that we have seen before, like to switch in protected mode, it becomes only 3 virtual machine exit to inject, okay? And so it's easier. And so it simplifies the injection of the inputs, so the generation of test cases. And so, but we have to understand if this replay works. So because we are doing a lot of modifications. And so in our evaluation, we show that by doing this replay, so reinjecting only the input to the hypervisor without the guest execution, we are able to cover the same code coverage. So the hypervisor does not detect these behavior. And the nice thing is that this implementation that we did, that was also intrusive because it was not transparent to the target, but we used, we modified the hypervisor by using a preemption timer in hardware feature to reinject the virtual machine exit. And so it's also intrusive, this solution, even though now we have a transparent solution in nested virtualization. The hypervisor was not able to detect this problem. Not this problem, so it was not detected as a problem, so it's a good thing. And then we have also gain in efficiency because, of course, we are injecting directly inputs and not, we are not spending time in doing operations in the guest virtual machine that are not useful for testing the hypervisor. And then we did our experiments. So, but even though our paper was more on recon replay, so we were able to reinject these test cases and also to discover new coverage. But we had the problem because, as you can see, we can have good crashes, so due to a bug, but we can have also crashes due to false positives because we have these two problems with our solution because from one side we are simplifying so we introduce this new concept, the new approach to inject inputs to the hypervisor, so directly in the hardware virtualization interface. But on the other side, on the other end, we have a problem. We can have a false positive because we are jumping the hardware checks. And so we can put whatever input we want without caring about the hardware checks. And so we can go to bug on and hardware faults that are not our goal. And so in this paper, Hypermirage, that is not our paper, they start from from our approach, but they use symbolic execution to reduce this number of false positives. And the second limitation instead is not covered from their approach. It's still an open limitation. So for instance, in our case, we used sequences of virtual machine exit to, so we infer stateful virtual machine exit from the nominal workloads, but we are not able to discover new stateful dependencies. So these are references. I don't speak about device virtualization. And so the generic takeaway of this presentation are three. The first one is about these new technologies that we have from hardware vendors, because for instance, my evaluation was MBA 1.0. Now we have MBA 2.0, and they improve. So probably the limitations that I discovered in MBA 1.0, now they are not, I know that they are not a problem anymore. And so, but anyway, we need systematic workload, a systematic evaluation for these controllers, and we cannot use just, like generic workloads for this controller. Then we saw also the problem of this trade-off, this balance between predictability and efficiency, because from one side, probably we say, okay, I introduce this technology to have guarantees on the worst case execution time, but on the other side, we risk that we lose in terms of efficiency, and this is not possible in cloud computing. And after, in addition, we saw also the security, that is another problem, because sometimes we can have, again, hardware feature like Intel VTX, virtualization technology, but we have still a software intervention, and we can have problems about security. And so this is the final takeaway. And these are instead the ongoing works that I'm continuing. So I was planning to extend my DSN paper, but there is this new paper 2026, 10 DSS. So what I'm doing is working on these 4 topics. The second one is trying to reuse our approach that is transparent to the hypervisor, is able to infer inputs from the guest execution to start concolic execution for the hypervisor about device virtualization. And then we have another problem that is not addressed in hypervisor security, that is reverse debugging. So there are several techniques at operating system conferences, NSDI, OSDI especially, about reverse debugging, so using recon replay, but not for the hypervisor. And we need, when we have a problem or we have an alarm, we need to reverse this behavior as soon as possible. And so it's a topic that is not addressed for hypervisors targets. And after another work on direction is creating, starting from CV, because now we have a lot of common vulnerabilities in these hypervisors, okay, like in device virtualization or in CPU virtualization. And we need to understand what are the common weaknesses of these vulnerabilities in order to prevent these bugs by using static analysis. And the fourth and last is we have other technologies. I don't know if you know, like Android virtualization framework in Android, that basically they start to create trusted execution environment by using a thin hypervisor. And so we have a different attack surface that we need to explore. So from the hypervisor versus the trusted execution environment. Thank you.
questions?
Oh, yeah, if you have a question, of course, yeah, open.
You know, it's a question to the audience. Do you have questions?
So I have one. Thank you for your talk. I was wondering, since the very first work that you were presenting, the first one, you were the motivation behind that was that you wanted to, let's say, transfer some tasks that are latency sensitive somehow, like robotics in the industry and these kind of things, to the cloud, right? And I was wondering if at the end you also made an evaluation of the end-to-end latency that you can improve with your system from, you know, the end robots or whatever, vehicular vehicles or whatever, to the data center where the task is running.
Yeah, it is a nice question. Thank you. No, I just focused on the node, so I didn't consider the end-to-end latency. So I didn't consider. I start from an edge node, and I see. First of all, because it's not easy, because you know that the network connectivity is also unstable. So we add another source of interference, and so I just focused on this source of interference.
Okay.
Yeah.
Thank you.
Thank you for the nice lecture. So I was wondering, I was told that just when there's several, you discuss this notion of workload, when there are many tasks allocated to this cloud computing, the simulation of the options for scheduling was extremely difficult. And that, because you have to represent exactly the resources that you lock and so what is the state of the art for these questions of just of the, I mean, assume you want to, you have a workflow which is given to you and you want to define this optimal scheduling with all the intricacies that you mentioned, namely not only the end-to-end delay being minimized, but also resources.
Yeah, understood.
So
Yeah, yeah, it is an orthogonal problem. So
Yeah.
the scheduling. I mean, I read some papers about at Eurosys especially about scheduling that they consider the resource utilization. So they consider like, for instance, they use performance counters to understand how many budget the application are using, and so you can do. So it depends, of course, from the purpose of the scheduling, because they assume that in these works that I read, they assume that you have at most one critical application running on the critical core. But I think it is an open problem, especially first of all because we don't know the sources of interference, so it's not easy to even though you create an algorithm, probably it's not easy to apply this algorithm because, for instance, these technologies are only on the Intel servers, and maybe if you go to R, you need to do other evaluation. So it's not easy. It's not easy to have to control these regulation. And once you know how to control this regulation, you can start. I mean, I told you it's orthogonal, I believe, right? Because you can assume that you have these regulation approaches, and then you can focus on scheduling. And in my case, I just focus it on the handling on calculating on inferring the sources of the indirect regulation, basically. But yes, I'm not expert about scheduling, and I read some papers, but I'm not I think it's still an open problem because I read this paper 1 year ago, 2 years, yeah, I think last year I read this paper at Eurosys. So it's an open problem.
Thank you.
I didn't follow all the details. I couldn't follow, but one of your findings is that to evaluate if this technology MBA behaves as expected, correct me if I'm wrong, but we need more workloads, more diverse workload, and maybe a workload that is designed to discover certain problem in this approach. So, and I wonder whether it is the way one should construct critical systems, because maybe I'm naive, but the critical system, I thought it should be constructed with some properties by construction that you don't need the right workload to see if this property holds or not. So if you tell me you can drive this car that is driven with the cloud, and we tried 1,000 combinations of workloads of the process running the car, and on the other processes running in the same machine on the cloud, we run 1,000 combinations, and it always showed this property. So you are sure you will survive. No, I will be scared because maybe the 1,001 combination of workload will be the one that will crash my car. So how come that these properties, even if they are designed for real-time and critical systems, they do not exhibit those properties by design and by construction? I don't know if my question makes the sense.
Okay. So yeah, in this evaluation, I relied on the incremental development and certification. That is basically you exactly reproduce the maximum interference, and for instance, the memory bandwidth interference on the other core. So you assume that you have the worst case, like for instance, on the other core. So you have a critical application on a core, on a physical core, and on the parallel core, I have this workload that run the worst workload to create this interference. Okay, in this way you can infer the worst case. The problem is that this worst case, for instance, for the memory bandwidth, if you have you have a workload that access to the memory, you have a memory fetching workload. Okay, for instance, for a critical task. The latency of this phase of the critical task increase proportionally with the number of contenders, and so is a problem. So if you assume the worst case and you don't bound, you don't put a bound on this worst case, you risk to have a very pessimistic worst case execution time, and so you lose in terms of resource utilization because you don't have the worst case every time.
Okay.
And I understand your point. You say, how can we be sure that this is the worst case? About MBA, it's a old work, but I remember that it was very good. So when you understand the behavior, and so you are able to describe really well in a predictable way the behavior, you don't find a lot of outliers. I mean, I think now I don't remember, but it was very stable. So it was yeah.
Empirically, it was very stable.
Sorry?
Empirically, it was very stable. I mean,
Yeah.
you observed that it was
Exactly. But yeah, I could say one outlier could be
fatal one.
yeah, but if you in that case, I think you can put, for instance, you can you increase the granularity. You can increase the granularity in this way. Probably you are able to lower these worst case. So instead of considering the worst case execution time for just one memory access, you can do a memory fetching phase that is a set of memory operation in consecutive memory operation to fetch the memory in cache. And in this way, I think the worst case cannot be on all the possible accesses on the memory fetching phase, and so you reduce the worst case, right? I think. But yes, I don't know. It's not easy. I didn't work on worst case execution time calculation by using like static analysis.
Thank you.
Okay, thank you. Thank you
Thank
for
the speaker.
the.
Ce le chiami?